Okay, welcome to a short video about creating and evaluating functions. Functions is just a fancy name for when you have a pattern that you can write a rule for. For example, last week, we were talking about sequences, and we saw that there's an adding or subtracting pattern, which meant it was an arithmetic sequence, or a multiplying pattern, which meant it was a geometric sequence. We could write equations for those, or we can write them in function form. So just a little bit of terminology here. The way that you say a function is in terms of another value. So this is the function c of a. So verbally what you say is c of a equals t. For this one, b of f equals a. So the value in the parentheses is the of part, and basically what this means is that your output, the thing in the end, depends on what your input is, what you're putting in. Let's look at an actual example. So to evaluate a function, there's some value you're putting into the function. Whatever's happening to it in there, you're adding to it, you're subtracting, you're multiplying it, maybe you're squaring it or taking the square root of it. So all sorts of different things. You can divide it, okay? Do all those things to whatever your input value was, and then it spits out the output. So here's an actual function. It might look familiar. It might look like a linear function to you because it's sort of in the form mx plus b. But instead of a y equals, we're just using the terminology f of x. So this function f of x equals 3x plus 4. And this here indicates my input. So this says, what if I put 3 into the function f? So f of 3 equals, and what you do is you take your function 3, but instead of where the x is, you're putting in your input. In this case, it's 3 plus 4, and we know 3 times 3 is 9 plus 4, and so my output is 13. For the next problem, it says put 7 into the function f. So I'm still using the same function. If I put 7 in for x, then that's going to become 3 times 7 plus 4. Well, that's going to be 21 plus 4. My output is 25. And lastly, what if I put a negative number in as my input? Same deal. Put in negative 4 in for the x. So that's going to become 3 times negative 4 plus 4, or negative 12 plus 4. Negative 12 plus 4, so negative plus a positive. That's going to leave me with a negative 8. Slightly different function. This one we're calling g of x is equal to x squared subtract 4. So this says, what if I want to put the 5, the value of 5, into function g? So what is g of 5? Well, that means I'm going to do 5 squared minus 4. Just a little hint here, I like to always put whatever my x value is in parentheses. I think it'll just help you along the way here. 5 squared we know is 25, minus 4, my output is 21. Looking at the second example, and here's why I was recommending the parentheses, what if I put negative 2 into the function g? So this is going to become negative 2 parentheses squared minus 4. Negative 2 squared, well, negative 2 times a negative 2 is a positive 4 minus 4. My output here is 0. The reason I recommended doing this in parentheses is because if you don't do parentheses, oftentimes if you tried to do that on your calculator, it would square the 2, but not the negative part. And so it would look like the answer is negative 4. But we know that we need to square the whole value, and the whole value in this case is negative 2. So negative 2 times negative 2, which is what squaring means, is a positive 4. If we put g of 11 in, that means it's going to be 11 squared minus 4. Well, 11 squared is 121 minus 4 is going to be 117 as my output. Now maybe you're laughing a little bit about this bottom one, but this says, what if I want to put g of big ape, monkey ape in here, okay? It's okay for the input to not be an actual numerical value. You're not going to be able to do much with it, but you can still input it into the function. So if I put ape man in here, and let's see how I do at drawing this guy. It's not bad. A little bushy tail there. Ape man squared minus 4. I can't simplify that anymore, but that's just my output. That's what I get out if I put in an ape. I get a square and minus 4 from it. So a little silly one there. All right, to create a function, you can take a story problem like this and put it into function form. So it says it's Yogi's birthday. Boo Boo gives him 5 picnic baskets to celebrate the special day. Every day after that, Yogi borrows 3 picnic baskets from unsuspecting campers. How many picnic baskets will Yogi have after 10 days? Well, the first thing to do is to create your function equation. So I might do P of B, picnic, how many picnic baskets, if we're putting in the number of baskets as our input. Oh, actually, I'm sorry. The number of days is our input. Excuse me. I should use D here. So picnic baskets after a certain number of days. Sorry about that. And if you've got 5 to start out, that's sort of like what we're adding on the end. Our starting value is 5. And 3 picnic baskets every day from campers. So that's going to be 3 each day. So my picnic basket function depends on the number of days. And if I get 3 each day and then 5 to start out, then that's how my function works. And then if I have an input after 10 days, then I'm going to be P of 10. So that's going to be 3 times 10 plus 5. Well, that's going to be 30 plus 5, or 35 picnic baskets. Nice. Here's another example. We have a gym membership plan, and it says per visit plan, monthly fee is $12, fee per visit is $3. Or you could use the unlimited plan, which is $60 to $65 per month. How would you decide which plan is best? This is where you need to decide how many visits you're going to have. So if you decide that you're going to go twice a week to the gym, and let's say it's a typical 4-week month, which means 2 times per week for 4 weeks, means you're going to visit the gym 8 times. So let's look at the 2 functions. It looks like the per visit plan, we'll say the gym membership per month-ish is going to be $3 for every visit. This is where I'm failing again. I'm so sorry. We want to make this a V because the variables in here need to match in here. So $3 per visit plus $12 per month. Or the unlimited plan will make P is just $65 per month. Just going to be 65 no matter what. Well, to determine which is better, you probably want to plug in the number of visits into the V here. So G of 8 visits is going to be 3 times 8 plus 12. Well, that's going to be 24 plus 12. which becomes $36. So if you're only going to visit 8 times, then the per visit plan is going to be a better deal. If you started to plug in different values, you would reach a point where the $65 ends up being a better option. But this is a way to compare different functions. And one more, I think, here. How many police officers in a city of 20,000 people? So it looks like we can find a function by looking at the pattern here. That's only adding 1, that's adding 4, that's adding 6, that's adding 15. Oops, hold on a second, someone's knocking at the door. Okay, sorry about the interruption. I guess it wasn't interrupting you because I paused the video. We were looking at this situation with the number of police officers in a city of 20,000 people. So here, if you have a population of in thousands, 10,000, 20,000, 30,000, 40,000, 50,000, how many police officers are necessary? And these are maybe examples. And hopefully you're looking at this table going, I don't see an exact pattern here. But what you do sort of see, and this is where we can start to approximate, because we know that not everything out in our world is exactly linear or exactly exponential. So we can approximate this as multiplying by 2, which means this is going to be an exponential function. So we're looking at something like f of x equals, let's see, if we worked backwards times 2, so we're starting with 1 times 2 to the x power. So we want to know how many police officers in a city with 20,000 people. Let's say we want to bump that population up. Okay, let's say that there's 100, we want to plug in 100 for x, 110,000. Okay, so the easiest thing to do at this point, rather than having to do it all out, is to go to a graphing calculator, or even a calculator on your apps that would show a table as well, and we're going to plug in 2 raised to the x power, and I'm going to go directly to my table, and you can see in the table, you know, if there were 6.5, so in 10,000s, so that would be how many police officers here. If I wanted to change my table settings, I could change it to start at, say, 10, and go up by 1s, and then look at the table again. So let's say when x is 10, y is 1024, but I think I said, what if it's 110,000? So I just want to point out this to you. This 1.3E30 is the calculator's way of doing scientific notation, 1.3E30. So if we go back to our notes here, when we plugged in 100, our output was 1.3E30. This is the calculator's way of saying 1.3 times 10 to the 30th power, which means I'm writing 1.3 and I'm moving this over 30 places. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That's only 20, and you can see I need 10 more. So it's going to be a huge number of police officers. So that doesn't make a lot of sense, because we probably don't even have that many. Well, we don't have that many people even in our world. So this is a situation where we started to model a situation with a function that we thought made sense, doubling. As your population increases, the number of police officers you need doubles. But there has to be a point in this graph, if it's exponential, where maybe it just needs to even out, that we don't need more police officers, more and more and more, because we're going to run out of people. So There are times when functions can represent situations to a certain point, and then they no longer are good representations. That's it for today. Remember function notation. This reads f of x, and maybe the equation is 5x squared. Whatever you plug in, x is your input. You also plug it into this part, and then you get your output. Have a great day.